Thank you for your introduction, Professor Hua. And good afternoon, everyone. My name is Yuankang Zhao. I'm a PhD candidate from University of Chinese Academy of Sciences and a research intern at Alibaba Group. And today I'm excited to present our work, MARC, Motion-Aware Rate Control for Mobile E-commerce Cloud Rendering. This is a collaborative effort with my colleagues from Alibaba Group and the University of Chinese Academy of Sciences. So today, mobile e-commerce is increasingly shifting from traditional text, images, and videos toward immersive 3D experience. So this allows users to engage with high-fidelity 3D models in real time on their devices. However, rendering this content locally present challenges, including limited computing power, storage, and limited battery life for mobile devices. To overcome this, cloud rendering has emerged as a compelling solution. The core idea of cloud rendering is to offload the computationally task to the powerful remote servers, and then stream only the resulting video frame back to the user. So this approach reduces the burden on the client and enables high-fidelity experience on any device. The user's quality of experience in cloud rendering depends on a fundamental trade-off between two conflicting goals. On one hand, we need low latency, the motion to photon latency, which means from a user's action to the visual feedback needs to be very low. Typically, it should under 150 milliseconds to feel responsive. On the other hand, we need high visual quality for an immersive and realistic experience, which generally require a higher video bitrate. So the dilemma is that increasing the bitrate to improve quality may inflate network queues and cause congestion, which in turn increases latency. Here's the typical architecture of a cloud rendering system, which is built on real-time protocols like WebRTC. The client captures user action, which we classify as either engage, meaning motion, or inspect, meaning non-motion, and send these motion messages to the server. On the server side, a 3D engine renders the graphics, and an encoder compresses them into a video stream. The resulting video frames are then sent out via a pacer, and the congestion controller estimates the available bandwidth and to avoid overwhelming the network. And our work focuses on the rate controller, which is the yellow box. It takes the bandwidth estimate and decides the target encoding bitrate, directly impacting the final trade-off between quality and latency. To understand what users really care about, we computed the average frame latency and frame bitrate for each session and performed a linear regression to reveal their relationship, as this figure shows. Our first observation aligns well with the intuition that a lower frame latency and a higher bitrate are associated with longer session durations, which means higher engagement. And we further make an interesting observation is that during motion phases, shown by the pink line, session duration drops much faster than as latency increases. In fact, the drop is 75% steeper compared to non-motion phases. The graph on the right shows a similar but less pronounced trend for bitrate. This leads us to our first critical insight for user QoE preferences are not static. They evolve dynamically with user motion. This observation leads to the requirement a rate controller should be motion aware to sense the motion phases in order to dynamically adjust the bitrate based on user preferences. Then let's dive into what users actually do. This trace plots frame size over time, and the pink bands mark when a user is in motion. Notice the clear on-off pattern with a short on burst of activity followed by a quiet off period. We measure the length of motion and non-motion phases. On the left, 74% of motion phases span just 2 to 4 frames. That's only 66 to 133 milliseconds. On the right, 70% of the pause lasts fewer than 15 frames. So users actually alternate between motion and the rest very quickly. So what does this mean for system design? Because user's state can change within a few frames, the rate controller must react at frame level. Ironically, motion frames, the user care about most, put the greatest strain on the network. As you can see in the frame size CDF on the right, motion frames, the pink line, are larger than non-motion frames. Actually, motion frames are 22% larger in size on average. This is because changing content is simply harder to compress for encoder. This large frame size directly leads to longer scene duration, as shown on the left. The 99th percentile scene duration for motion frames is 1.9 times longer than for non-motion frames, creating significant tail latency. This leads to our third observation. Despite the same target bitrate given by the rate controller, motion frames tend to have larger frame size and longer scene duration than non-motion frames. This brings us to a critical QE mismatch. Remember our first observation that users are most sensitive to latency during motion phases. Combining with our third observation, we find that latency spike often occur when users are most sensitive to interaction delays. So this observation leads to our requirement 3, which calls for differentiated bitrate assignment for motion and non-motion frames. So to summarize the problem, we have identified a fundamental and ironic mismatch. We have seen that users are most sensitive to high latency during their interactions. However, it is precisely during these motion phases that current systems deliver the worst performance, with longer frame latencies. Existing rate controllers use the same logic for both motion and non-motion phases. So our research goal is to design a motion-aware rate control, or MARC, that dynamically aligns the bitrate decision with these real-time user QE preferences to maximize the overall quality of experience. And here is our system design for MARC, which directly implements our 3 design principles. This entire control loop operates on a frame-by-frame basis to enable rapid adaptation. Let's walk through the flow of a single frame. First, to achieve motion awareness, the system receives motion information from the user, which feeds into our state predictor. This component forecasts future user behavior and network conditions. Then these predictions are sent to our QE optimizer, which is the core of MARC. This is where we make our frame-level differentiated bitrate assignment. The result is the target bitrate, specifically tailored for the next frame. This is sent to the encoder. And I will explain them in more detail. The state predictor's job is to forecast the near future state of the system. And its most critical task is to predict user motion. Our key insight here is that while users' first action is random, once they're started, their motion tends to be continuous. So based on this, we built a lightweight Markovian model. It analyzed the state of the last few frames to predict the probability of the next frame will also be a motion frame. So the motion transition probability are learned directly from our large-scale online dataset, which makes the online prediction extremely fast and efficient. In addition to motion, the predictor also forecasts network conditions. It simply uses recent historical values for round-trip time and pacing rate from the transport layer, because our measurements show that these are quite stable over a short period. And the QE optimizer is the brain of MARC. Its job is to translate our observation insight into a dynamic mathematical objective that we can optimize. This is our objective function shown at the top. It balances the reward from quality against the penalty from latency. The critical innovation here is the latency penalty item. We use a motion indicator, MI, to apply a higher penalty weight to motion frames. This increased penalty is calibrated directly from the findings of our large-scale user study, reflecting our discovery that users are much more sensitive to latency during interactions. Our quality and latency functions themselves are designed to reflect user perception. For example, capture the diminishing return for higher bitrate. By formulating the problem this way, we can use stochastic optimization to find the best bitrate for each frame. A key question here is, why do we need to consider a window of future frame instead of just making a best decision for the very next one? The answer lies in that we call frame size delay cascade. As this diagram illustrates, the center queue is dynamic. If we choose a higher bitrate for the current frame, it makes it larger. It doesn't just increase its own send time. It also builds up the queue, which increases the waiting delay for all of the subsequent frames. To account for this, MARC's optimizer uses an n-step look-ahead strategy. It solves for the optimal bitrate for an entire window of future frames to maximize their total combined QoE. We first evaluate MARC in a trace-driven simulation environment, replaying real-world network and user motion traces from Taobao's production system. We compared MARC against baselines, including WebRTC, SQP, Adaptive, and models of commercial applications. And this plot shows the trade-off between average bitrate and the 95th percentile frame latency. As you can see, the baselines scattered as individual points and MARC, represented by the dashed line connecting different configurations, traces out a clear superior Pareto frontier. This means that for any given latency, MARC achieves a higher video bitrate, and for any given bitrate, it achieves a lower tail latency. And of course, the ultimate validation comes from the real world. We deployed MARC in a massive A/B test on Taobao's platform, involving over 1 million user sessions. As you can see in the box plot, when combined to the default WebRTC, MARC's reduced the average session stop by 71%. And more importantly, this improved performance translated directly to a better user engagement. With MARC, users' interaction time increased by 20%, and the average session duration grew by 9%. This shows that users were not only staying longer, but were also actively engaged. So what's the cost of these gains? On the client side, there is zero overhead, as MARC is an entirely server-side solution. On the server, the computational cost was negligible, adding only 1.3% overhead increases per session. So, to conclude, our contribution is threefold. Through a large-scale measurement study, we discovered that user QoE preference is not static. It evolves dynamically with user motion in cloud rendering. Applications. Users are most sensitive to latency during interaction, which is precisely when existing systems deliver the worst performance. So we proposed MARC, a motion-aware rate control framework. It uses behavior modeling and dynamic QoE optimization to align bitrate decision with real-time user needs. We deployed and validated MARC in a massive production environment where it significantly reduced session stalls and measurably improved user engagement, demonstrating its real-world effectiveness. Okay, that concludes my talk. Thank you for your attention, and we'll be happy to take any questions.